afternoon, everyone. I am Shubhanu Haldar. I am a PhD student of IIT Delhi. So, I will be your TA in this course. So, today we will be discussing about the questions of BFS and DFS. So, we'll be starting soon. So, today my camera is not working. Maybe there is a technical issue. Okay, so we'll continue right now. Yeah, Abhishek, chup, dhire. Okay, so as you know, like every week, as we start with some questions, so I request everyone to try to solve the questions by yourselves, and then try to put the answer in chat. Then we'll discuss how to solve the question. Okay. So our first question is about the breadth-first search algorithm. So which has been implemented using the queue data structure. So we know that BFS is implemented using queue data structure, and DFS is implemented uh, using the stack data structure. So the question is, which one of the following is a possible order of visiting the nodes in the graph below? So like you can start from any node, maybe A, maybe N, or maybe O. Then you have to find that possible BFS, like breadth first search traversal order basically. So the the best option will be the starting from any node like M, N, or maybe you can substitute the answer. Okay, so first please try to do it by yourself. पूजा, थोड़ा सा धीमे बात करोगे ना, थोड़ा अच्छा होगा. Okay, so if we start from the first option. Okay, so our first option is here it is telling that start from N. So as you know that for BFS we create a array which is for visited. Okay, and we create a queue data structure basically which basically indicate the that we have explored the node or not. Okay, so if we start from M, and if we go with this option, so if we start from M, so you can write it like this is M, N, O, P, Q, R. Okay, fine. So first M is all are 0, all are initially 0 because we have not visited any node. Okay, so first what we'll do, that we'll visit the M node, so it will be 1. Okay, then what we'll do, that we'll in the queue we'll push the neighboring nodes. So which are the neighboring nodes? One is N, Q, and R. Okay, it is N, Q, and R. Okay, so from this neighboring node we will be going to other neighboring nodes basically. So if you go with this option M, N, O, P, Q, R, so you can see that N is fine, it's like in 1 hop distance, Q is in 1 hop distance, and R is in 1 hop distance. But you can see that this is NOP, but O is 2 hop distance from M, so this option is not correct. Fine. So if you come to the second option, it is saying that NQMPOR. So okay, so if you start from node P, if you start from this node according to second option. If you start from this, so in your queue, your neighboring node will be M, okay, O, Q, and that's it. M, O, Q. Okay, you can see here. Here it is saying that if you start from N, then it will be Q, M, P. But P is not this P. P is not in the Q. Okay, because it's not in one hop distance from N. So this option is also not correct. So here we are basically substituting our options. So we'll be go with this option now, that is third option. So if we go with the third option, it is saying that start from node Q. Okay, we'll start from node Q and see what happens. So if we start from node Q, okay, then M, N, R. So we can go M in one hop, N is also one hop, but R is not one hop distance from Q. Okay, so which are in one hop distance from Q? That is M, N, O, and P. So this option is also not correct. So if we start from, if we take this option, P, we have to start from P. Okay, so if we start from P, then our option will be O, Q, N, M, R. So in our queue, what will be in our queue? In one hop distance, we have O, Q. Okay, O and Q. Fine. O and Q is fine. Okay. So if you go to Q and so from this queue basically, we will be taking one node and we will be exploring their neighbors in one hop distance. So next we will be going to Q. Okay, so Q is popped up from this queue, and what will come in the queue next? The neighboring node of this queue. So which are the neighboring nodes which is not visited yet? That is N and M. So N will come here and M will come here. So here N has come and M has come. Okay, so if we take from the queue, if we pop up this M and try to find the neighbor of M, then we can see we found R. So R is also visited. So R is here. So now, so this basically P, O, Q, N, M, R, P, O, Q, N, M, R is basically the valid BFS. This is the basically. So our question was the which one of the following is the possible order of visiting the nodes in the graph below. So this is the possible order of visiting the nodes on the graph. Okay, so option D is the correct one. So this is our second question today. So given the graph G, so if you start DFS from node A, then which sequence is not possible? So I will help you to give the graph. This is for DFS. Okay, so this is for DFS. So I will give you the graph now. So the graph is given like this is A. Okay, this is B, this is A, this is B. Okay, so I hope the question is clear to everyone that so this is the given graph. So if we start DFS from node A, so this is our starting point, then which sequence is not possible? Okay, so in DFS, you know that we start from a node and push them into a stack. Okay, so how basically we do it? Like we have a stack like this. Fine. You can draw a stack. Okay. So this is the endpoint of the stack. So first we have node A. We have to start from node A. This is given in question. Okay. So our node is basically A. Then we will be finding our neighboring node, that is EBF. Okay. Fine. Okay. So this can be of any order. This can be of B, E, F, or this can be of F, E, B. But we'll that doesn't matter basically, because whenever we do the whenever we progress, you can see that this ordering doesn't matter really. Okay. So we can start from, so after A, so all in the all option, all are starting from A. Okay. So we can start from B and we can start from F both. So in the neighborhood of A, we have B and F both. So first try to start with F. Okay. So we are trying to start with F. So from this one. Okay. So in stack F will be coming, and what will be there in one of this time, that will be, or maybe we can start from because the most options is from B itself. Okay. So we can start from B. Okay. From here. So what will be there? There will be A, E, F, H. Okay. So A, E from B, in one half distance you can go to A, you can go to E, you can go to F, and you can go to H. Fine. So that's why I have pushed them into that stack. Now what I can do, that I can see that A is already visited here. Okay. So I can go to node E. Okay. If I push the node E, what will be the neighborhood of E? Like one half distance from E, it will be G, B, and A. Okay. This will be A, B, and G. Okay. So can anyone please confirm that am I audible or not?
Audible, sir.
Okay, fine. So A, B, and G is in one half distance from E basically. Okay. So now A is already visited, you can see from here. B is also already visited, you can see from here. So now you have only option to explore the G. So I am again so the stack will grow like this, but as there is a short of the space, so I am creating the stack here. Okay. So now you will be exploring the node G. So if you come to G, what is in your one half distance? So in G you have E, H, F. Okay. And from V, so E is already visited, and H is H you are visiting. Okay. So if you visit from H, so you can go to B, G, and F. B, G, and F. And from next is your B is equal to F. If you visit from F, you can find A, B, H, G. A, B, H, G. So this will be your stack. So now compare the options one by one. So A, B, E, G, H, F. Is this possible? So A, you can go to B, then E. If you can go to E, then G. Yes, G is possible. Then H. H is also possible. Then F. F is also possible. So this is possible. Okay. So you can check the option B like this. So A, B, F. From A you can go to B. From B you can go to F. Okay, from F you can go to E. From F, no, you can see in the neighborhood of F there is no E. Okay, so this, I think this will not, this will be the our answer, that this sequence is not possible. So let's also try to see the other sequences like C. So that is C is possible or not. So you can check by graph also, like you can find by visiting the graph. So if you start from A, so you can come to B, yes, in one of, then you can come to F in one of, fine, then you can come to H in one of, fine, then you can come to G in one of, fine, then E. Okay, so okay, so you can complete all the notes like this. Okay, so now we have the fourth option, so this is also possible. So now the fourth option is A F B, like A you can come, then F you can come, then B you can come by one of distance, then from B A F G. So from G you can come, like this one I am following, A F G H B E. So after G you can go to H, fine, then you can go to B, fine, then you can go to E, fine. So in this order you also can find the sequence. Okay, but the sequence is not possible, that is A B F E H G. Okay, why? You can see from the graph also, like if you come to, if you follow this A B F E H G, A B F, fine, from F you can't go to E, so there is E is not in one of distance of F, so that's why this sequence is not possible. Right? So this is the question 3, that what should be the appropriate data structure for graph traversal using BFS and DFS. So please try to type your answer in the chat box. So this is a very easy question, so please type the answer in the chat box. Yeah, so so Anil Kumar is saying that option A is correct, that stack for BFS and Q for DFS. Okay, okay. So our first two question was from, one was from BFS. So this was from BFS. Okay, and this question was from DFS. Here you have seen that how I was following the algorithm and doing the traversals. Okay, so I clearly mentioned here that for BFS you are mentioning the queue data structure for storing the unvisited nodes. Okay, so I showed you here. Okay, so for BFS you are using the queue data structure, but for DFS you are using the stack data structure. Fine. Yeah, Sonu, your answer is absolutely correct. Yeah, so B will be the correct answer. Q for BFS and stack for DFS. So this is the correct answer. Fine. So this was an easy question. So next, move on to the next question. So question number 4. So what you have to do, you have to that assume that you are performing a BFS on this graph. So this, your graph is given. Now on this graph using a queue data structure, so of course we already learned that if you are doing the BFS algorithm, if you are running the BFS algorithm, you will be using the queue data structure. So how many unique breadth first search orderings are possible on the graph? Like if you start from here, you can go to here, then go to here. Okay, fine. Like if you start from here, so what will be your neighboring node? Your neighboring node will be this one. So then your neighboring for these three will be your neighboring node. Like you can first you can go to here, then second you can go to here, then third you can go to here. Or or first you can go to here, second you can go to here, third you can go to here. So what will be the, how many possible like how many unique, how many unique breadfast ordering are possible on this cup? So this is the question. So please try to put your answer on the chat box. So basically what happens that you can select any of the node from the outside node. Okay, so maybe you are selecting this one. Okay, so if you are selecting this node, then what will be the neighboring node in one of distance? So this will be the neighboring node in one of distance of this red one. Fine, from this red one. Okay, so from this green one you have three options. Okay, from this green one you have three options, like 1 2 3, or 3 2 1, or 2 1 3. Okay, so how many options you have already? So from this one how many options you have? Like where you are standing here. Okay, so you have three ways to go, so total 3 factorial options you have. Okay, got it? This is basically 6 options you have. Okay, so if you have 3 factorial options for this node, so like, so the outsider nodes, there are total 4 outsider nodes. Like you are starting from this node, but you could have start from this node also, you could have start from this node also, you could have start from this node also. So that's why total 4 into 3 factorial. So what will be the answer? 24. Okay, so do you think that this is the correct answer? So please anyone, like, please try the question and please type any answer in the chat box. Like this is a multiple choice question, that doesn't matter that you are doing it correct or wrong. So like you can type anything, like just from your intuition only. Okay, so I have shown you that you can the question is, if you start from any node, okay, if you start from any node of this graph, okay, so how many possible BFS you can find? Okay, BFS ordering basically. So I showed you that you can start from any node of this 4. So can't you start from this node? So you can start from this node also. Okay, so if you start from this node, how many options, how many paths are open for you? So as I told you, like if you were standing from here to here, you had 3 paths. So like 3 choices, so total 3 factorial paths were open for you. So now you are basically at the middle position. Okay, so if you are in the middle position, then how many options are open for you? That is 4 factorial. Okay, so 4 factorial, what is 4 factorial? 4 factorial is 4 factorial 24. So total how many choices you have? 24 plus 24. Why 24 plus 20? Total is equal to 48. So this is the correct answer. Why 48? Because you can start from any outer side node. Okay, that's why you have 24, and you can also start from any inner start from the inner node. So that's why this 24. Okay, so total the answer is 48. Got it? So if anyone has any question, any doubt on this, so please raise your hand, or maybe you can unmute yourself and tell me. Yeah, please.
Sir, can you explain with some other example, sir, please?
Yeah, sure.
Thank you.
Well, So okay, so basically what happens there, so if you were here, so you have two choices. So you are here, so you can go here or here. So how many choices you have? You have basically two factorial choices, that is 2 into 1. Is it correct or not? So this is correct. So now you have, you are here, now you can go here or here or here. Now how many choices you have? So what will be the ordering of you? So here your option was 2, basically because you can first visit this node, then second visit this node, or you can first visit this node, then secondly visit this node. So you have only two choices. So but in this situation, how many choices you have? If you are, if you are here and you have road like from your front, from your left hand side, and from your right hand side. So how many ways you can visit three places? So this is your home maybe, so this is the market 1, this is the market 2, and this is the market 3. You have to go everywhere, okay, market 1, market 2, market 3, to collect your groceries, and you have to come back your home, okay. So how many possible options are there? So you can first visit this one, then okay, so first visit this one, then secondly visit this one, then third visit this one. Or you can first visit this one, then second visit this one, then third visit this one, okay. Or you can first visit this one, then second visit this one, then third visit this one, fine. Then so how many possible options will be there like this? So,
Three factorial.
yeah, so that's why,
Okay.
I told this. So there are 4
Okay.
into 3 factorial. Like if you start from this node, you have 3 factorial choices, okay. If you start from this node, you have also have 3 factorial choices. If you
Yes,
start
sir.
from 3 node, this, so that's why 4 into 3 factorial choices, for because you can choose any of the outer node, okay. So that's why 4 into 3 factorial, that's why 24. And
Yeah.
if you also, this middle node is here. So if you start from this middle node, you have how many choices? You have like 4 way you can go. So that's why you have 4
Yeah.
factorial choices, which is also 24. So that's why total 24 plus 24, 48 choices.
Okay.
Yeah,
Okay. Thank you, sir.
welcome. So now this is the question that so we have already seen the question about the DFS, like so you can consider a DFS of an undirected graph with 3 vertices P, Q, and R. Okay, so please read the question carefully. So you have 3 nodes, this one, and this one, which is basically node P, node Q, and node R. Okay. Now what is saying that let discovery time du represent the time instant when the vertex u is first visited. Okay. So you will be traversing using the depth first search. Okay. So this dp, basically the time, tells you the time when you first visited this node, and fu is the finish time, like this, like when you last visited this node. This represents the time instant when the vertex u is last visited. So this is the time instant is given, okay. So you first visited p node at 5 unit, second you first visited q node at 6 unit, and like this you last visited p node at 12 units, and you last visited q nodes at 10 units. So what is true about the graph? So from this DFS traversal, you have to basically judge that how the graph will look like, okay. So you know that the the uh, the DFS, for DFS we use the stack, Okay, I have already shown you. Okay, so what can we do here, like for this, to solve this question, what can we do here? Like you can see that the time instance are given, so we can sort it out, the time instance. Like 5 unit is here, okay, 6 is here, okay, something also happened at 10. I'm just writing by sorting the timings, okay. 12 is here, 14 is here, and 18 is here. Okay, fine. Now we'll see that in this time instant what happened. In 5 unit of time, dp happened. Okay. For 6 unit, dq happened. Okay. For 10 unit, okay, fq happened. Okay. For 12 unit, fp happened. Okay. For 14 unit, dr happened, and 15 unit fr happened. Okay, fine. So please try yourself, that try to think yourself that what is happening here. So so look at the options, that p is connected to q and r. This is the first option, p is connected to q and r. Okay, and this is the second option, r is connected to q only. Okay, we'll see that how this is happening. So we know that this is DFS traversal, and we know for DFS we use stack. So first we have seen the p, so in stack we can put p. Okay, now we have seen q, so we have seen q, so from p we can go to q. Okay, so we have seen q, then q is the last visited one. So like this is the last visited one, so q will be popped up from the stack, and this place will be this place now is empty. Okay, because you have already last visited a q. So basically you can see that from q you can't go to r, okay. So now you have seen that at 12 unit of time, you have also last seen the p. So p is not in the queue, not in the stack. Now what is coming in the stack? R is coming. Basically in place of p, the R will come, and at 18 unit of time, R will also pop up. Okay, so this is happening. So when R is coming, nothing is in the queue. Okay, so if p is connected to q and r, so p is connected to q and r, but we can see that p is not connected to r. Okay, otherwise r should come when p is already in this stack. Now r is connected to q only. We have seen that q is not connected to r. Okay, the graph has two components. So as this is given that this is an undirected graph. Okay, so for understanding, I draw the directed edges, but this is an undirected graph. Okay, so you can see here that there are two modules, like there are two components, PQ, one is PQ and one is R. Okay, so this will be the correct answer. The graph has two components. Fine. So now this is the question, that how many elements can be there in stack in the worst case if you start traversing from any node using DFS. Okay, so let me give you a graph structure. So if you have given this graph structure, so what will be the, so you know that you will be starting from this node. Okay, maybe you can start from any node, but I encourage you to start from this node, counting from this node, because maybe in solution I will be showing you that what happened if you start from this node. Okay, if you start from this node, then you push them into your stack. Okay, okay, as I have shown in the previous question, that p is there, q is there. Okay, but when r came, nothing was in the stack. Okay, so what happens, if you do the DFS traversal, how in worst situation, how many possible elements can be in your stack at a time. Okay, so basically the in depth first search traversal depth will be very high if number of nodes between two nodes is very high. Basically it means that depth of the stack, so this is basically the depth of your stack. Okay, this will be very high when distance between two nodes, okay, number of nodes between two nodes is very high. Okay, so here our objective is to finding the longest path between two nodes. Okay, so how we will start, so we can start like, so this is our first node, so this will come to stack, fine, no issue. So then this will be our second node, this will also come to stack, this will be our third node, this will come to stack, this will be our fourth node. Okay, this will come to stack, this will be our fifth node, so this will come to stack. Now this will be our sixth node, this will also come to stack. Now you can see this, that this node you can visit later. Okay, so you can now from 6 we have, because this is neighborhood of both 2 and 6, so now you can come to this node from here to here. Okay, now this one, so this node also you can visit later. Okay, so now you are coming to this one from 10 to 11, then from 11 to 12, okay, 13, 14, 15, 16, 17, 18, 19. Okay, so you can see from this node to this node, in between you have total 19 nodes. Okay, if you skip these two nodes, nothing matters. Okay, so there are total 19 node is possible, like in between these two nodes. Okay, so how many what will be the, our question is that what will be the how many elements can be there in stack in the worst case if you start traversing from any node. Okay, so if we start traversing, 19 nodes can be there, because whenever you have already seen this. Okay, so in your stack what happens, that whenever you are already seen this, this will be pop up. So you have seen that whenever q is done, q will be popped up. So this will be 19 will be popped up, then 18 will be popped up, 17 will be popped up, 16, 15, 14, 13, 12, 11 will be popped up, then you will come to 10. Okay, so whenever you will come to 10, you have to go to the visit, you have to visit this one. Fine, so this node will also be visited, but the space here, so space of these nodes will be empty. Okay, so that's why this will not, this for this node you don't have to allocate extra space. Okay, so maximum 9, if you have 19 element are here, so you can accommodate 19 element in a stack. That is enough for you, because already when you will come here, some element will be already deleted, this element will be already deleted from your stack. Okay, so now you will be come here, this will be popped up, this will be popped up. Whenever you will come at 6 node, you will see that, oh, I have a node in my neighborhood. Okay, this is not already visited, so you will be visiting this node, and your computation will be done, and this will be popped up, and 6 will be also popped up. Then 5, 4, 3, 2, 1. So got it? How the 19 is coming? So 19 is the correct answer. Okay.
Sir, here the
Yes, 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 please.
can I ask a question, sir?
Yeah, sure,
Please.
sure, sure, sure.
Yeah, sir. Here you have taken this graph. If I take some other graph, I get different answer. No, sir.
Yeah, of course. So what will be the answer? Like so basically
Uh,
so basically our question is, main our motive is basically to
uh,
find the uh, in our situation how many element can be there in the stack. So
okay.
our graph can be anything. So what I have to find,
Uh,
basically, if I take this graph, so I have to find the
uh,
distance between two nodes. So
okay.
distance between two nodes mean number of nodes in between these two nodes. Okay, so you can see
Oh,
1, 2, 3, 4, 5. Okay,
uh,
so of
uh,
course 5 nodes will be here in OS situation. But if you
oh,
have this node here, or you have
uh,
this node here, so whenever first you will visit this one, first you
mm,
will visit this one. This will be you into this will this these nodes will be uh, 1 2 3 4 5 6, up to 6 will be in your stack. So now you have
yes,
seen that from neighborhood of 6 there is no node, so this will be popped up, so this will be popped up,
okay.
so this space
Uh,
will be empty for you. For 5 will be
uh,
popped up, so this space will also be empty for you. 4 will be popped up, this space will also be empty for you. 3 will be popped up, 3, this space is already empty for you. So not 3 basically. So in 3 you will be seeing that, okay, in my neighborhood already 7 and 8 is there. Okay,
uh,
7 and 8. So your 7 will come here and 8 will come here. So this is not taking any extra space. This
uh,
the space was already there. So that's
oh,
why the in our situation, how many basically the what will be the number of elements in this stack, that is basically distance between two nodes. So
okay. Sir, but here, how we will come to know which graph we have to select?
so graph will be okay. So graph is already given, like, so
Uh,
graph is
Okay,
already
if
given
it
to you.
is given, it's fine.
Yeah.
If it is not given, then if we want to find the minimum, then how it will be, sir? Can how the graph will be taken care?
Okay, so for this case, like, whenever you will be doing the DFS or BFS, your graph
Uh,
will always be given.
okay,
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 like,
sir. Okay,
every case the graph will be given. Okay.
okay, sir.
um,
Uh,
so here you have to take the decision, like, here you have to find the maximum number of
uh,
maximum distance between two nodes basically. So you can see that
okay.
to find the maximum distance between two nodes, you can't start from here because you already have this node. Okay, so you have to start from
Uh,
this edge. Okay, so then you can see that one node, two node, three node, and four node. That's how.
yes, yes, sir.
Yeah.
Oh, yes. Okay, sir.
Okay, thank you,
Thank you.
thank you, thank you.
Thank you so much.
So this is the next question number 7. That if a DAG is given, so I think you all have read about the DAG, that directed acyclic graph. Okay, so if a DAG is given, then find out the possible topological sorting sequence. Okay, so I'll draw the DAG for you. Okay. So till now we have seen that the BFS and DFS we have performed all was on the undirected graph, but for topological sort, we must have a directed acyclic graph. Okay, directed acyclic graph means that we have a directed graph, like we know from which node to which node we have to come, and acyclic means there must not be any cycle present in this graph. So you can see that in this graph we don't have any cycle present. Okay, and all the edges are directed. Okay, so now what will be the possible topological sorting sequence in this case? Okay. So if I write the algo of the topological sort, please try to solve by yourself and put the answer in the chat. Also you can follow my writing that what should be your thinking process, that how you will think to solve this question if this kind of graph is given and you have to find a topological sort. So you have to follow some algorithm. Like, what is the algorithm? That first you have to identify the vertices that have no incoming edges. Okay, fine. Now can you identify any vertices from this graph that has no incoming edge? So you can see that this V2 and V5 has no incoming edge. Okay, fine. So I think this much you can do. So is there anyone who found the answer? You can write in the chat box. So basically it is saying that, so this is your given DAG. Now you have to find the topological ordering. Okay, and you have to follow this step 1 and step 2. Step 1 is saying that identify the vertices that have no incoming edge. So this V2 and V5 has no incoming edge. Okay, so these two can be your option. Like, so you can see this V2 and V5 here. So these two can be your option. Okay, but we have to verify the rest of the answer. You can see that V6 and V3, V6 has two incoming edge and V3 has two incoming edge. So that's why these two cannot be your correct option anyhow. So what you have to do next? So you can start from V2 or you can start from V5. Fine. So if you start from V2, now you came to you came here, which is uh, V1. Okay, but before finishing the V1, you must have to finish V5. Okay, because you can see here, delete this vertex of in degree 0 and all its outgoing edges. Okay, from the graph, place it in the output. So this V5 has no in degree, so you have to place it in the output. Okay, if you start from V5. Okay, and what is saying, delete this vertex of in degree 0 all its outgoing edges from the graph and place it in the output. So from if you come to V1, you must have to process the V5. So V5 is here. So if you start from V5, you also must have to process V2 here. So first I am going to this one, V2 V5. Okay, fine. So from V1, where you can go, V2 V5 is done, you can go to V7. Yeah, you can go to V7. Fine. So from V7, what you have option? You have seen that you have option V3 and V6. Okay, so you can go to V3 and V6. Okay, so this is our correct answer. Fine. Now we check from V5. So V5 is done, you come to V1, but before V1 you see that V2 has no in degree, it has only one out degree. In degree means so out degree means one node is going outside. Okay, and in degree means something is coming. So in our algorithm it is giving even that delete this vertex of in degree 0. Okay, so this vertex has no in degree. Okay, because nothing here is coming. Okay, so that's why we have deleted this and put in my output. Okay, now we can see V1 is coming. Just a second. Now you can say V1 is coming, and then V7 is coming, then we can go to V3, and then we can go to V6. Okay, so rest all are fine. So V5, V2, V1, V7, V3, V6. So V5, V2, V1, you can go to V7, then V3, then you can come this. So this A and C are the correct option, correct topological ordering is here. Okay. So now we have to find what will be the data structure used and the time complexity in the program, basically like for okay. Let me check that. Yeah, basically for this topology in this program means basically this topological sort. So how can you do this algorithm basically? So you have this graph. Okay, you have this graph. Okay, so if you have this graph, so you can make a linked list from this graph: V1, V2, V3, V4, V5, V6. Okay, so these are the nodes, and this basically are the links. Okay, so from this link we can find that, so from V1 who are connected, V2 and V, yeah, So from V1, who are the basically we are linking from V1 here. So that is basically the we are finding the out degrees. Okay. So from V1 the out degrees is here V from V3 and V7. Okay. From V2, is there any out degree? Yes. From V2 the out degree is V1. Fine. Nothing is there. From V3 out degree is V6. From V3 out degree is V6. Okay. From V4, so okay, so V4 is not here. What we can do? We can do V5, 6, 7. Okay, 4 is not here. Change to 5, 6, 7. So from V5, out degree is V1. Okay, from V6 there is no out degree. Okay, so it is null. So from V7, out degree is V3 and V6. Okay, so these are basically out degrees. As you have find the out degree, so you can see that to run your algorithm you have to you also have to found the in degrees. So that's why you have to create another array of in degrees, in degree array. Okay, now in your in degree array you have node number 1 2 3 5 6 7. Okay, in your in degree array, first all are zeros. Okay, first all are zeros. Okay, then what you will do, you will count the so for V1 how many nodes are here? So basically 2. Okay, so this is your in degree counter. Got it? So it will have 2 in degree. Okay. Is it having? Okay, yeah. 2 in degree. For 2, how many in degrees are here? For V2, 0. For V3, there are 2 in degrees. 1 0 2. You can check from here. So this is how this is happening. So if you use a linked list structure and a array to for the in degrees, so you can finish this algorithm in order of V plus E, because for creating this array you need order of V time. Okay, and because in degree array will be equal to number of nodes, and for this one there you can find that all are basically edges. So these are basically order of, this will be how many edges can be there? There can be 2e number of edges. Okay, so because for any node like for any node from this will appear 2 times. So basically order of V plus 2e, so it will come like order of V plus E. Okay, so this is here. The next question is the number of different topological orderings of the vertices of the graph is. So how many different topological orderings of the vertices is possible from this graph? So this is a DAG, no problem, because this is directed. Okay, so you can see that you have to start from A and finish at F. Okay, start from A and finish at F. So A is here and F is here. So in between, how many options are there basically? So that you have to find basically. So what will be the in these blank spaces? So blank spaces in here, in blank spaces you can have B, C, D, E basically. So you have four space left. So how many here, if we start from A and end with F, so we have four possible in between options. Okay, so blank spaces are to be filled with B, C, D and E, such that B come before C and D come before E. Okay, so number of ways to arrange B, C, D, E such that B come before C and D come before C, like B must come. So here the thing is, B must come before C because C is at last, and D must come before E. Okay, so these two are the our restrictions. Okay, so what will be possible option? So it will be 4 factorial by 2 factorial into 2 factorial. Okay, which is 6. Or otherwise, if you don't want to try this option, so what else you can do? So 6 is the answer we have seen. That what else method is possible without this permutation combination? So you are starting from A. Okay, so you have gone to B. So or you have gone to D. So from A, B and D is your option. So you can go to B and you can go to D. So from B you can go to C or you can go to D also. From B you can go to C also or you can go to D also. C also and D also. From D you can go to E also or B also. Okay, fine. So if you are coming from like if you are here, you have seen A. Okay, now you have seen D. Okay, so what are the possible options for you? You have possible option that you can go here or here. Got it? So that's why these two are options. Okay, if you have seen E, you have only option that you write B, C, because F is the last one. So before F you have to write B and C. So before F you have to write B and C. Fine. Now there are two options after B. So after now what is the situation? That is, if you first you have seen A. Okay, so we will be coming to this point, ADB basically. We have seen this point A, we have seen A, we have seen D, now we have written B. So for B you have two options. You can go to C, either C or either E. So from here also you can go to C or E. Okay, so if you go to C, if you go here, then F is the last option, so you have to write E. So that's why if you go C, then E is the last option, you have to write E, or C or F. Okay, for this one, if you go to A, B, C, if you go to A, B, C, then you are coming to F, but before F you have to finish D and E. So that's why D and E have to finish. For A, B, D, okay, for A, B, D, you have two choices, C or E. You have two choices, C or E. So what you can do, that you can write E, F, or this one can be C, F. So see, there are 6 choices. Okay, so these are the two possible solution of this question. Okay, so now come to this one. that is question number 10. So the question says about that which one is following one is true, that the graph doesn't have any topological ordering, or both the topological orderings are correct, and which you have to find the topological ordering of this graph basically. So what you can do, so you can choose any node like which has no incoming edges. So you can see that P node has no incoming edges and S node has no incoming edges. Okay, so you can start from any of these two nodes. Okay, P or S, fine. So you can start from P or you can start from S, fine. What you will do, you will apply depth first search by choosing any of this P or S node. So as vertex gets a finishing time, assign it to head of a linked list. Linked list if you require topological ordering. So basically what you have to do, so you are starting from here P. So from P you can see Q. Okay, fine. But before writing Q, you can see that R is there. Okay, so R is also has incoming edges from P, and it has also has incoming outgoing edges to Q. So after Q, you can write this one. Okay, PQ. Okay, so if you write PQ, so this is not possible because S is you must have to write R here. So you must have to write R here. So this is not possible. So what can we do? So this is not possible. PQRS, because before P you must have to write R. Okay. So what is possible? So after P you see that you are coming to Q, but S has no incoming edges, so you have to write S. So after S you can write R. Okay, then Q will come because everyone is pointing to Q. Okay, so Q will be at the last. Got it? So if you are starting from S, what will be the possible order? So if you start from S, so you start from here. Okay, so you may go to R, or you may go to Q. So maybe you go to, so our option is S, P, R, Q. Okay, so if you go to P, so is P is the correct one. So from R, if you go to from S, if you come here, so before writing this R you have to write the P, because P has no incoming edges. Okay, so you have to write the P. So P is written. Now you can write R, then Q. So as you see that Q has all the incoming edges. Okay, so Q is always will be at the last. So these two options are correct. Got it? So now question is, the most efficient algorithm for finding the number of connected components in undirected graph on n vertices and m edges has time complexity. So how can you find the number of connected components in an undirected graph? Okay, which has n vertices and m edges. So I have shown you the example of undirected graph and component already, which was this one. So if you remember this one correctly, you can see that what algorithm you used here. You used DFS here. Okay, and you found that there are two components. Okay, so basically so if you have a three component graph, how three component graph will look like. So this is one component, this is one component, and this is two components. So if this is your graph G, then this is your three components. This is first component, second component, and third component. Okay. So how you will how which algorithm can find your so if you apply BFS, so you apply BFS here. So you will, from here you go to one of distance, fine. So from here you will go to one of distance, from here you will go to find one of distance. But so this will not will not be a possible. So BFS also can find BFS and DFS. BFS and DFS both can find the number of connected components. So using BFS you can also visit all the nodes. So using DFS also you can visit all the nodes. So how will you do? So first you choose any vertices. Okay. So maybe you are choosing these vertices. So from these vertices you can go to any one of these. Okay. Whenever you finish this, so you will have a array which is named as visited. Okay. So that will have all the, so this is 1 2 3 4 5, these are the node numbering basically 9. Okay. 8 9. Okay. So you know you will be initializing or visited as 0. Okay. Whenever you will be doing depth first search, so in your DFS algorithm, so you will be coming to this one and this will be 1, then you will be coming to this one, then this will be 1, you will be coming to this one and this will be 1, fine. Then you see that, oh, my this node are not yet visited. So you will be running the DFS algorithm while you don't get the visited array as all ones. Okay. So what is the best time complexity for this DFS algorithm, BFS and DFS? So in both scenario the best time complexity is order of V plus E. Okay. So there are two scenarios, like you can use the so you can use the adjacency matrix or the adjacency list. Okay. So you can use adjacency matrix or adjacency list. Okay. In both scenario, in matrix you will get order of V square and you get order of V plus E. So V here V means M and N means, so this is the correct answer. Okay. So we'll see like, well, the next question is basically this one, like why the algorithm is basically order of V and order of V. So for adjacency matrix you have to create a matrix like this, and which is of 1 to V and 1 to V. Okay. And here you will have 1 1 0 like this is a adjacency matrix. Okay. So if your two node is connected, like this is node number 1 and this is node number 2, okay, then this will be 1. Okay. Otherwise all will be 0. So this is the concept of adjacency matrix. And adjacency list means, okay, so your one node is connected to two nodes, then you will have a linked list. Okay. If your node is connected to two other nodes, then you will have a linked list. So this is the adjacency matrix and this is the adjacency list. Fine. So what will be the time complexity using the adjacency matrix and adjacency list? So if you try to find the adjacency matrix, always you have to run for all vertices, and you have to find all the rows. So that's why it is order of V square. And for adjacency list, you will create a visited array which will take order of V time, and because you know that this adjacency list are 2e number of linked list, so that's why your timing will be order of V plus 2e, which is order of V plus E. So this is the alpha. So b square okay. Now the question is a connected graph, a connected undirected graph G has 2775 edges. Okay, what can you say about n, the number of vertices in G? So how many number of edges are there in the graph? 2775. Okay, and what can we say about the n? What if there are 2775 edges, then what will be the number of vertices there? So that's the question basically. So how many types of graphs are there? So if you see that, okay, so you know the do you know the concept of complete graph? So complete graph means every node is connected to every node. So here you can see every node is connected to everyone. So if the node is 4, how many edges are there? Number of edges is equal to 1 2 3 4 5 6. And if number of node is equal to 3, if we have 3, so how many edges are there? 3 edges. Okay, like this, like if v is equal to 5, how many edges will be there? It will be n into n minus 1 by 2. Okay, so if this is 5, so we have according to this formula we will have 10 edges like this. So we have five vertices. If we connect each one with each one, okay, so you can see that how many edges we have now. 1 2 3 4 5 6 7 8 9 10. We have 10 edges. Okay, so for complete graph, what is the number of edges? For complete graph, number of edges is equal to n into n minus 1 by 2. Okay, and for okay, so you know the about the tree. So if we have a tree, if tree has three nodes, three child, so it has three edges, 4 node with 3 edges. It has 2 child, 3 node with 2 edges. Like you can see here, node number is equal to 1 2 3 7, but edge number is equal to 6. Got it? So always v minus 1, e is equal to v minus 1 for the case of tree. Okay, and what was in the case of complete graph? It was n into n minus 1. So why I am saying this? Here it is saying that a connected undirected graph G has 2775 edges. And what can we say about n? So that means we have to find out the maximum, find out the graph where maximum edges is possible. So in complete graph, maximum edges are possible, and in tree, minimum edges is possible. Okay, so that's why we have taken these two examples. So if you see that, so a tree with 2776 vertices has 2775 edges, as I have told you, like this one. Okay, and a complete graph with 75 vertices has 2775 edges. Like how? 75 into 75 minus 1 by 2, that is 75 into 74 by 2. So this is basically 2775. So what will be the correct answer? N is equal to 75 less than 75 and greater than 2776. Okay, so this is the correct answer of N. Okay, now the second question is, an airline serves 1000 cities and runs 5500 directed flights each day between these cities. So aeroplane is like there are cities, many cities are there. Okay, okay. So and the aeroplane run between these cities. Okay. So basically, their cities being the vertices, and aeroplane. Uh, so how many vertices are there? 100. And how many direct flights each day? That is 5500. So this is basically the edge of our graph. Okay, between these cities, which of the following is a good data structure to represent the correction of time? Okay, so please try to find the answer by yourself. Okay, and write it in the chat box. So this is from your previous year's question paper. So you must be able to solve this question. Like at least try it by yourself. Okay. So please look into the options. And what are the possible cases here? Like you can represent it like an array. Okay, where aij is equal to 1 if there is a direct flight from city I to city j, or 0 otherwise. So this is basically the adjacency. So option A is basically the adjacency matrix. So if this is a adjacency matrix, so how many entries will be there? So how many cities are there? So array will have 1000 by 1000, so it will have total like 10 lakh entries. 10 lakh entries will be there. Okay, so how this is saying that in adjacency matrix will be there. Okay, from each city to, like maybe from Delhi, Kolkata, Mumbai, Jaipur, or maybe Chennai. Okay, so here will be same Delhi, Kolkata, Mumbai, Jaipur, Chennai. Okay, so this will be your array. Okay, so if there is a direct flight from Delhi to Kolkata, you will have 1, rest are zeros. Okay, now if we have direct flight from maybe from Delhi to Chennai, we also have a flight. Okay, so like this. So here, maybe here, this one, because Delhi to Kolkata you had a flight, so you will have 1 here also, rest are zeros. Okay, like this you have to fill it. Okay, so this will be your representation of your data. So but in this scenario you have 10 lakh entries will be there. Okay, so so what will be the then our option is the stack containing values ij for each pair of the cities ij for which there is a direct flight. So then the second option B, is suggesting to create a stack. Okay, So create a stack. Okay. Now, what should be the in this stack? So stack containing ij for each pair of cities, like ij for Delhi to Kolkata, for Kolkata to Mumbai, for Jaipur to Chennai, for Chennai to Mumbai. So you have to put like this. Okay. So how many options will be there? So if you follow this data structure, like stack data structure, you can't search like this. Like you can't search anything. Like you have to find whenever you are using a data structure, you have to search from that data structure. Like if there is a here in this scenario, you are what you are saving in the data structure, you are saving the collection of flight. Okay. So if you save like this stack, so for to access the stack, what you have to do? To access this stack, first you have to remove this element, then you can access this element. You can't directly access this element, because in stack first you have to remove this element, then you can access this element. So that's why using the stack data structure here is a very bad idea. Also same thing for the queue. Okay, same thing for the queue. So you can access this point without accessing this or this point. Got it? So that's why what we can do, we can find a linked list. As the question is suggesting. So question is suggesting that a list containing value ij for each pair of cities I and j for which there is a direct flight. Okay, so this will be your I. Okay, so this will be your Delhi, Kolkata, Mumbai, Chennai, Jaipur. And if you have a direct flight from Delhi to Mumbai, okay. Gosh, if you have direct flight from Delhi to Mumbai, then you can do like this. Okay. Then if you have direct flight from Kolkata, you can do like this. Okay. So this means that you have direct flight from Delhi to Mumbai and Delhi to Kolkata, not Mumbai to Kolkata. Okay. So this is like this. Okay. So the linked list will be the best representation for your data structure. Okay. Now come to this question. So the question says that you have given the graph. Suppose you obtain the following BFS tree rooted at node J. So your root node is node number J. For an undirected graph with vertices this one. Okay. Which one of the following cannot be an edge in the original graph? So here, so this is a tree. This is not a graph. So this is a tree. But this tree, from where you got this tree? You got this tree from the BFS traversal. Okay. So you maybe basically previously you had a graph like this. Okay. So using this graph, if you traverse this graph using the BFS algorithm, you get this tree. Okay. So what cannot be the edge in the original graph? So this is the question. So in BFS, what you do basically, if you start from this node, so first you try to find the all nodes in one hop distance. So you can see these, all these green nodes are in one hop distance. Okay, so if you name it A, B, C, D, E, F, G, H, I, J, then you can find that if you start from node A, okay, then you can find that you will be getting B, D, E and C. B, D, E and C, right? B, D, E and C. So now what you have option, you can go to B. From B you can go to J. Okay, so this is done, these two nodes are done. Okay, now you can come to D. Okay, fine, D has nothing. Okay, now you can come to C. Okay, C, from C you can go to F and G. C you can come to F and G. Okay, and from E you can go to H and I. Okay, so I'll draw this in a good manner. So this is our complete graph display. Okay. So what you can see that A is at the root level. Okay, now all the levels in one hop distance are in same levels. Like this is level 1, this is level 2, and this is level 3. Okay, so these are all in same level. Okay, so this is B, C, D, E, B, E, C, D are in same level. So as you can see, in graph structure also this is in same level, and in tree structure also this is in same level. Also you can see that this J is after B. Okay, so here will be J will be here. Okay, so this J, H, F, J, H and F. Okay, something is wrong here. Okay, let us draw again. So from E, where can you go? So from E you can go to H. Okay, only H. Okay, from C you can go to F. Okay, from B you can go to J. Okay, from H you can go to I. Okay, from F you can go to G. Okay, so you can see the nodes in same level are in basically so in an undirected graph, all non-tree edges must be at the same level or between adjacent level. So if you see here that CG, C and G is in same level, fine. BK, B and K, okay. B and K is not in same level. Okay, then B and A and D, okay. So basically if you want to reach from, so you know that CG, so this C and G is in same level, fine, no problem. So this can be a like here, like this B and D can be edge. Yes, B and D can be edge here. Okay, so also like B and K, like B and K, so like uh, uh, E and H, so E and H is already a edge here, so this also can happen. So B and F, so B and F, like B and F, like E and I. So from E to I, so according to this, these two cannot be H, B and F, and AD can be H, A and D can be H. So the right option is B and F. So this is saying that in an undirected graph, all non-tree edges must be at the same level or between adjacent levels. So BF is an edge across two levels. So BF is an edge across two levels. Okay. So that's why. Basically, okay. So now the question is this one. So we are interested in topological ordering of the following DAG, which satisfy the constant that whenever 9 appears after 8, 2 must appear after 4. How many such orderings are there? So we can see that there are two blocks are in parallel here. So 2 or 3 4, like in topological ordering you to go 2 or 3 4, or you can go 6 7 8 or 9. Okay, these 4 can be reordered. So please first try yourself, then I'll say. So first try to find out the number of ways of reordering the blocks. Okay. So left block means this one. So this can, so we can write like 6 9 7 9 or 8 9. Okay. And how many ways we can write this one? We can like 2 3 4 then 5. So here end is 10, you know that end is 10, here also you know that end is 5. Okay, so you can write 2 3 4 or or 342 or uh, or what we can write 234 342 or 324. Okay. So basically here we have uh, three orders, and here we have three orders. Okay. So look at the conditions. Okay. So the conditions are, whenever 9s appear after 8, 2 must appear after 4. Okay. So this 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 was our situation. So if 9 appear after 8, and so how many cases 9 appear after 8? Okay. Like you can write like 6 8 9, or 6 7 9, or 6 7 8 9. So this will be the or you can write like 8 or 9. These are the cases. So remember the constant, that whenever 9 appears after 8, 2 must appear after 4. So this will be the case. So this situation will not be possible. 2 must appear after 4. 2 will be at the last. So this is right. This is wrong. Okay. So this is our constant list. So what will be the answer? So if there are two blocks in parallel, 2, 3 and 4, you can see here, this one and this one. Okay. And if and 6, 7, 8 and 9, and that can be reordered. There are 4 ways of ordering the right block, of which only 1, 6, 7, 8, 9 has 9 after 8. Okay. Our constant was which satisfy that 9 after 8. Okay. Now there are 3 ways of ordering the left blocks. Okay. Which is only 1, 3, 4, 2, which has 2 after 4. So there are 3 possibilities. Okay. For unconstant topological orders, so these are the 9 possibilities for constant topological order. Okay. And 1 for unconstant. Okay. So total 10 possibilities, 10 topological possibilities are there. So 10 orderings will be here. Okay. So this is our last question for today. So applying for permits to put up a factory is an 11-step process. Okay. Okay. So some steps depend on others as observed below. Okay. So basically you can see that if you apply for passport, you have to first go to passport office, then you also have to go to for permit for police station. So there are steps after some steps. Okay. So you cannot like override any step. So every step you have to follow. So in here also like it is saying that applying for a permit to put up a factory is an 11 step process. So this is your constant. So using this constant you have to draw something, like, okay. So like here it is saying that each step takes a week to complete. So there is a process. So each step takes 1 week to complete the process. So what is the minimum number of weeks required to get all the permits in place? Okay, so this is the question basically. So you can draw here. You can see that. So the hint of to answer this question is that you can draw a directed acyclic graph from this. Directed because you know that step 1 must be complete before step 3. Okay, so if this is step 1, this must be complete before step 3. Okay, now step 2 must be complete before step 3, 6, 7, 7 start. So step 2 must step 2 must complete before 3. Okay, 6. Okay, and 7 also. Okay, so am I right? Like step 1 must be complete before step 3 and 4. Oh, step 3 and 4 also. So step 1 before 3 or 4 also it must complete. So step 2 must complete before 3, 7 and 6. Step 2 must complete before 3, 6 and 7. Step 3 must be completed before step 7 starts. So this is the step 7. So there is a relationship. And from this diagram, so please try yourself to complete this diagram. So please try to complete the DAG as per the given. So if anyone has completed the drawing the DAG, please let me know in the chat. So here, so we completed this step 1, step 2, step 3. Okay, so for step 4, what is saying? Step 4 must be completed before step 5 start. So we can put here step 5. Step 4 must be completed before step 5 start, and step 5 must be completed before step 7 start. Okay, fine. Okay, now step 7 must be completed before step 8 and 9 start. So step 7 completed before step 8 start and step 9 start. Fine. Now step 9 must be completed before step 10 and 11 start. So step 9 also must be completed before 10 and 11. Fine. Now you have this DAG. Now from this DAG, what you have to find? What is the question? That each step takes a week to complete. What is the minimum number of weeks required to get all the permits in place? Okay. So this is a DAG. So this is the main part of this question, to build this DAG. So what will be the typical longest path? So you have to basically longest path mean, so from 1 you have to start and you have to reach either 10 or either 11. Okay, so basically if you reach here up to 9, if you reach here up to 9, if you start from here 1, and if you reach here 9, then you will, this boat will take one week. You can finish 10 also, and within 1 week 10 and 11 both will finish. Okay, so main we have to find what will be the, so 1 we know. Okay, then we know 9. Okay, then from 9 we have two options, 10 or 11. So we are taking maybe 10. Okay, fine, because this will also take 1 week. Okay, fine, you can do 10 or 11, both will take 1 week. Okay, so what you can go, so if you go to from 1 to 4, so it will take 1 week. Okay, from 4, from 4 no incoming edges here, you can go to 5, so you can go to 5, so 1 week. From 5 you have to go 7. Okay, from 7 it will take 1 week. Okay, from 7 you can go to 9, so this will take 1 week. So maximum, how many weeks it can, you can take? 1 2 3 4 5 total. No. So basically each step is 5 weeks. So 1 2 3 4 5 6 total 6 week you need. Basically for completing, to complete step 1 you need 1 week. For to complete step 2 you need step 4 5 you need 1 2 3. So this thing is called, so not in between. Basically to complete this, the whole process, you need 1. So that's why total from this node, from node 1 to, from node 1 to node 10, total we can see, total, including 6 1 and 10, we have 6 nodes. So that's why 6 we need. Okay, so fine. So this was the question I prepared for this week. So if anybody has any question in mind, please let me know. If anybody wish to ask anything or not. Please let me know that if anyone has any doubt.
Sir, how we will take this traveling, sir? Because 1, 4, 5, 7, 9, 10 or 11 that we are taking.
Yes.
So the path, I can take 1, 3, 7 and 9, 10.
Yes. Okay.
Ah,
So you are saying that you could have taken that this part 1 3
yes, sir. 1, 1,
1
3,
3
7,
9 and 10.
9, 10.
Yeah, you are right. But see,
Ah,
in topological ordering, so before
ah,
writing these 3, you must have to finish this 2. Okay, so this can be possible. So for, because when I wrote the algorithm for the topological sort, so there I wrote that delete this
Then,
vertex of in degree 0. So this vertex number 2 has in degree 0. Okay, so you have to delete this and write this here, then you can come to 3. Okay, then you can come to 7. Okay, so to come to 7, you have you also have to write this 4 5 and 6. Okay,
ah,
so then you can go to 9 and 10. So you can see here, like 1 2 3 7 9 10. So this could have also be an option, and this is also a 6 week, 1 week,
yes,
2 week,
ah,
3 4 5
ah.
6. Okay, so these both two, this both answer are same basically. So that's why
Okay,
we,
that way also I can take.
yeah.
Yeah, that's why, because anyway that if I calculate also, it should come to 6 weeks minimum.
Yes, minimum 6 week. Like less than that,
Okay.
you can get like 1 3
Yeah, we
1 3
cannot.
7 9 10 is not
Uh,
possible. Yeah.
yes, sir. But how about 279, 27910, sir?
Okay. Okay. So you are telling that
Two, 27
2 7.
9 10
Yeah.
9.
Just give me a second. 9 10. Yeah. So in
Mm.
this case, so if you start from here, okay, so
Mm-hmm.
you have to, if, so if you start from here, you'll be going to this one 7. Okay, so for 7 to write 7, because it all has the incoming edges. Okay, so you have to come here, you have to write 5. So you can come from 2 to 7, because for 7, if you do DFS, like before completing the 7, you have to come from here, like you have to come from 1 3 7, then you can come to 9. Or you can come from 2 1 4 5, then 7. Okay, so this part you have to follow. Okay, so if you see here that after 9 you will get 10 only, here also 6 week. Or if you see
Okay.
that 2 1 4 5 7, then you can go to 9, then to 10 or 11. Here you will be getting 7, more than 6 week
7.
basically. Yeah.
Okay, okay, okay. So I cannot take 6 because there is no incoming.
Yeah. Yes, 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 yes. This 6, this 10, this
Uh,
11, because this step is not depending to anything basically. Okay, so these are
okay.
independent, so that's why.
Okay, okay. Dependent, what it is that we have to take.
Yeah,
The
yeah.
priority is like dependent, which is
Yes,
which
exactly.
we have to take it.
Exactly,
Okay,
exactly.
okay, sir. Okay, thank you, sir.
Okay.
Thank you so much to understand.
Yeah,
Okay.
thank you, thank you. You are welcome. Okay, so if you have any
Mm.
question, please write your question in the comment section of your NPTEL. Okay, so I'll try to answer your question. Okay, thank you so much.
Sir, tomorrow is the last day. Tomorrow we can give the answers, no, sir, for the quiz.
Yes, yes, tomorrow you can give the answer.
Okay, we can change it and we can give. Tomorrow till evening we have time.
Yes, yes, yes.
Okay, okay,
Okay.
sir.
Thank you so much.
Thank you, sir.
Good, good.